A warm greeting to all. Today in this video we are going to discuss about fast Fourier transform FFT algorithm, and these are all the remaining modules in unit 3. So let's start with the introduction on DFT algorithm. So we know the formula for DFT, that is x of k equal to summation n varies from 0 to n minus 1 x of n e power minus j 2 pi by n into nk, and we know the limits for both k and n varies from 0 to n minus 1, so both are having finite length of sequence, and we are going to denote that finite length by capital N. So the limits are varying from 0 to n minus 1, and now we can do some other modifications in the general formula. It is nothing but the twiddle factor. So we are going to replace this term by twiddle factor w suffix n. So this is the example for x of n and example for x of k. So this is a sampled signal, discrete time signal, and this is the discrete frequency signal x of k. And this is a general formula. We all know x of n is the input, x of k is the output, that is in the discrete frequency form. It is the frequency time form, right? And wn is the twiddle factor. So if suppose if we are going to expand this equation, we can expand like this. And if you for a single value of k, we are having the n values from 0 to n minus 1. So we are having the expansion in the row wise as well as in the column wise, because we know the limit for k. K also is having n length, so we have to find n number of values for k. So starting from 0 till n minus 1, we will be having n values for k. So now the next what we are going to do is we are just going to check the performance of the DFT algorithm. So for checking the performance of the DFT algorithm, we are just going to calculate how many number of multiplications and the additions required to achieve such manipulation in the DFT algorithm. Say for example, so for finding a single value of k, how many multiplications we required? This is one of the multiplication, x of 0 multiplied with twiddle factor, right? So likewise up to n minus 1 we are having such repetitions in the multiplication. So we can say in general we are having up to 0 to n minus 1 we are having. So we can say we required n number of multiplications to find the single value of k, right? And for finding a single value of k, the additions required are n minus 1 multiplications. Say for example, if you are having 5 numbers in your hand, if you want to add those 5 numbers, and the number of additions we required is we have to sum up the numbers and by repeating the addition process by 4 times. If you are having a 10 number, if you want to add all the 10 numbers, then we have to do that addition process by 9 times. So if you are having, so in general we can say if you are having n numbers in your hand, and if you want to add all the n numbers, so we have to repeat the we have to do such additions by n minus 1 terms, right? So for finding a single value of k, we require n minus 1 number times of additions and n times of multiplication. So if suppose if you are going to find the value of k until its finite length, it means if you want to find the value of k starting from 0 to n minus 1, it means we are having total length as n. So for n, for single value of k, we required n multiplication and n minus 1 addition. So for n values of k, the number of additions and multiplications will be n times of n minus 1 addition and n times of n multiplication, right? So these are all the performance. So for doing such DFT algorithm, the performance, that is multiplication required is n square, n times of n, that is n square complex multiplications, and n times of n minus 1 addition, that is n into n minus 1 complex additions we require. So these are all the performance based on the number of samples for number of multiplications and number of additions. So if the sample is keep on increasing, the number of multiplications and the additions required is also it will take time. So to be more precise, we can say if there is more number of samples, the computation time will get increased, because we are having n square multiplications. You suppose if the n is say for example, if we are having the value of n as 1000, and for 1000 we required 1000 times of 1000 multiplications. So likewise 1000 into 999 times of additions. So it is keep on increasing. So you can say that in a single word that the time consuming for DFT algorithm is more, because we are requiring more number of multiplications as well as more number of additions. So the problem is we are having we require more time to do such DFT algorithm. So is there so the thing next what we have to do is we have to check for whether we can reduce the number of multiplications and additions we require to do such DFT algorithm. Yes, the answer is yes, we can reduce the number of multiplications and number of additions. So for reducing such number of multiplications and additions, we are the scientists arrived with some algorithm called fast Fourier algorithm. It has been designed and discovered by Cooley and Turkey. Both scientists have found that algorithm. It is one of the advanced, there is a fastest version of DFT algorithm. And remember, this DFT is a transformation. For transforming this time domain to a frequency domain, both are in discrete, we require this DFT, the discrete Fourier transform. But whereas that fast Fourier transform is not a transform, it's just an algorithm. It is this algorithm is used to improvise the performance of the DFT algorithm. So the main thing is the FFT is not a transform like Laplace Z transform. It is just an algorithm to improvise the DFT transformation, that is a process of performance of DFT. Okay, so now we'll discuss about the FFT formation in the next video. Thank you.